One very important aspect about the density matrix representation is that different ensembles of states can lead to the exact same density matrix. So, for example, we looked before at the density matrix for a maximally mixed state of the form 1/2 0 0 plus 1/2 1 1. And when we write this down in matrix form, we have 1/2 of the matrix 1 0 0 0 plus 1/2 of 0 0 0 1, which leads to the diagonal matrix 1/2 1 0 0 1. But now let's imagine we have a completely different preparation, a different ensemble of states. Let's say we have the state 1/2 state plus, and then 1/2 state minus. Now, if we look at this in matrix form, this gives us 1/2, and what is the density matrix for the plus state? Well, it's 1/2 1 1 1 1, and then plus 1/2. And the density matrix for the state minus is 1/2 1 minus 1 minus 1 1. So then if we multiply these halves, we get 1/4. And then if we add each of the elements in these two matrices, we get 2 0 0 2, which gives us the matrix 1/2 1 0 0 1. So here we can see that these two different preparations of having with classical probability 1/2 state 0 or state 1, or with classical probability having state plus or state minus, gives us the exact same density matrix, making it non-unique. Now you might say, well, maybe this is the case because this state is formed by 0 and 1, which are orthogonal states in the computational basis, and these ones are state minus and state plus, which are orthogonal states in the Hadamard basis. So maybe this is a very special case, but this is really not true. We can have, for example, a state of the form rho equal 1/3 0 0 plus 2/3 1 1, and then a completely different state of the form 1/2 state A plus 1/2 state B. So here we can see that these two states have completely different classical probabilities. And then if we have that A is of the form 1/√3 0 plus square root of 2/3 1, and B is 1/√3 0 minus square root of 2/3 1, we can show that this also results in a density matrix of the form 1/3 0 0 2/3, which is the same we have here. So then we can ask the question, well, what type of ensembles of states generate the same density matrix, and how are they related to each other? So we can show that if we have two ensembles, so let's say we have an ensemble of states with probabilities p sub I and states psi sub I, with I going from 1 to n. And here I've changed the nomenclature a little bit with respect to what we've used before. Before I used to denote the ensemble of states with associated probabilities as two separate lists, but here I'm just grouping them as pairs, and I think it's obvious what it means. So let's say we have this ensemble that generates a density matrix rho for I equal to 1 to n of each of the states psi sub I, weighted by the classical probabilities p sub I. And then let's say we have another ensemble of states with probabilities q sub j and states phi sub j, with j from 1 to m, that generates the density matrix j from 1 to m of q sub j phi sub j. So we can say these two matrices, rho and kappa, are equal to each other if and only if we can represent each of the elements in one of the matrices. So let's say the elements in rho weighted by their probabilities. So let's write that down. If we can say that each of these p sub I outer product of psi sub I with itself can be expressed as the sum of all the elements in the other density matrix up to some unitary transformation. So here we have each of these p sub i's, phi sub i's can be expressed as the sum of j going from 1 to m of q sub j times some unitary, let's denote it as I sub j, of phi sub j. And then here we have to take the transpose conjugate because we're working with density matrices. So if we can say that each of these elements here can be expressed in this form, then we can guarantee that these two matrices are equal to each other. Now, in textbooks, you will see this equality expressed in the form square root of p sub I, phi sub I, equal to the same sum, j from 1 to m, of square root of q sub j, uij, phi sub j, which is perfectly equivalent to what we have here, because this p sub i's and q sub j's are real numbers. So when we do the outer product between this side with itself and then this side with itself, we get to the same relationship we have here above. Now I wanted to express it in this form above because it shows us the direct relationship between these representations in density matrix form. Now, here we're not going to go over the proof of this equality. I believe it's relatively simple, and you can find it in chapter 2 of the Nielsen and Chuang textbook. But we can look at an example to show that this holds true. So we can go back to the two ensembles we had above. So we had rho equal to 1/2 of state 0 plus 1/2 of state 1. And we had this other ensemble of 1/2 of state plus 1/2 of state minus. And then to show that these two matrices rho and kappa are equal to each other, we have to be able to express each of the elements of one of the matrices in terms of the elements of the other matrix up to some unitary transformation. So let's take, for example, this matrix here, and let's try to express these two terms as a function of the terms in the matrix rho. So this first term here, well, this will correspond to some q sub 1, phi sub 1, and this is some q sub 2, phi sub 2, right? And if we use now this expression here, not the one with density matrices, but the one with the state vectors, well, we can say that then this q1, phi 1, and then we have to take the square root here, can be expressed as the sum of, well, rho has only two terms, so it will be square root of p sub 1 and then psi sub 1 plus square root of p sub 2, phi sub 2, right? So now let's replace with actual values here. So if we're going to focus first on just the plus state, well, we have then square root of 1 over 2. So this is for this 1 over 2 right here. And then times state plus. And then what is p sub 1? Well, it will be this 1/2 here. So square root of 1/2. And what is psi 1 is the state 0 plus square root of p2. What is p2? This 1/2 here. So 1/2. And then what is psi 2 is state 1. So now we need to show that this relationship holds up to some unitary transformation. So we have to write down here a u sub 1, 1. And here some u sub 1, 2. Right, so here the 1 over root 2's cancel, and we have that the state plus must be equal to this u11 state 0 plus this u12 1. Now here we know that if we apply unitary, let's say u11 to state 0, well, that's going to result in an arbitrary state of the form alpha 0 state 0 plus alpha 1 state 1, and the same for this u12 applied to state 1. We end up with another arbitrary state of the form beta 0 state 0 plus beta 1 state 1. Now if we replace state plus in the computational basis, we have 1 over root 2 0 plus 1, and then replacing this two terms here with our arbitrary states we have. So now what we can do is equate the terms associated with this state 0 from this side with the ones on this side, and the terms with state 1 on this side with the ones on this side. So that gives us two equations. 1 over root 2 has to be equal to alpha 0 plus beta 0. And then 1 over root 2 has to be equal to alpha 1 plus beta 1. And then we also have our normalization condition, right? We also know that alpha 0 norm squared plus alpha 1 norm squared must be equal to 1, and that beta 0 norm squared plus beta 1 norm squared must be equal to 1. So we have four equations with four unknowns. Now, because alpha 0, alpha 1, beta 0, beta 1 are complex numbers, these four equations result in many different solutions, but we can just pick one of them. Picking one of the real value solutions, which is of the form alpha 0 is 1 over 4 root 2 plus root 6. Alpha 1 is 1 over 4 root 2 minus root 6. And beta 0 is 1 over 4 root 2 minus root 6. And beta 1 is 1 over 4 root 2 plus root 6. And this works, right? So if we add the terms that go with state 0, which are alpha 0, beta 0, and add the terms that go with state 1, which are alpha 1, beta 1, well, this gives us 1 over 4 root 2 plus 1 over 4 root 2. Well, that's 2 over 4 root 2, which is the same as root 2 over 2, which is 1 over root 2. And then this plus root 6 minus root 6 cancel, and same on the other side. So here we can see that this probability amplitudes do add up to give us what we had here on the left side, which is the state plus. So now all we have left is to take these equations here that relate these arbitrary states with probabilities alpha 0, alpha 1, beta 0, beta 1 to some unitary transformations u11, u12, and try to find what this unitaries are. And I've already gone through the work of doing that, and if we apply a u11 that is an RY gate with an angle of theta equal to minus pi over 6 to our state 0, that provides the state with probability amplitudes alpha 0, alpha 1. And if we have a u12, which is a RY gate with theta equal to pi over 6, and if we apply that to state 1, that gives us the probability amplitudes beta 0, beta 1. So in summary, what we have done here is we have shown that at least this state plus with a probability associated with it of 1/2 can be expressed in terms of the terms 1/2 0 0 and 1/2 1 1 up to some unitary transformations u11, u12 that are given by these rotations here. Now, what's missing here to show that these two matrices rho and kappa are identical to each other? Well, now we need to find that the state minus with probability 1/2 can also be expressed in terms of these terms 1/2 0 0, 1/2 1 1, but it should be obvious that we can follow the exact same procedure to get those numbers. Now, another scenario where this ambiguity shows up is when we have, for example, a pure entangled state. So we've looked at the case where we have the state psi of the form 1/2, state 0 for Alice, state 0 for Bob, plus 1 for Alice, 1 for Bob. And we said that, well, if Bob receives this qubit but has no idea that this is an entangled state, all he can really say about his qubit is that it's represented by the density matrix of the form 1/2 1 0 0 1. And same for Alice. If we apply this concept of the partial trace and find the reduced density matrix for Alice, we get the exact same result. What if Alice and Bob now share a different pair of entangled qubits of the form 1/2, 0 for Alice, 1 for Bob, plus 1 for Alice, 0 for Bob? Well, if they are aware that their qubits are entangled, these two states are clearly very different, right? If they perform measurements on their qubits and then compare notes, in the first case, they're going to find out that their two qubits are perfectly correlated to each other. Whereas in this second case, they find out that their qubits are anti-correlated with each other, right? So in the first case, every time Alice measures a 0, Bob measures a 0, and same for the 1 state. But in the second case, when Alice measures a 0, Bob measures a 1. So they're perfectly anti-correlated. But if we look at the reduced density matrices for this state chi, well, they're of the same form. This rho sub b is also 1/2 1 0 0 1, and rho sub a is also 1/2 of 1 0 0 1. And this is very interesting, but it kind of makes sense, right? If, let's say, Bob only has information about his qubit, has no idea what's going on with Alice's qubit, well, all he can really see is that he gets the state 0 or the state 1 with 50% probability each. And it's the same for when we have this state psi up here. So there's no way for him to know any different. Now, this is very closely related to something known as the HJW theorem, where H stands for Hoxton, J for Josa, W for Wooters. And sometimes this is also known as the GHJW, and here G is for Jisin, or the SHJW, where this S stands for Schrödinger. Now, what this theorem says is very similar to what we've seen here, that that we can have several entangled states that result in the same reduced density matrices. Now, what this theorem is about is it's usually stated the other way around, that given some density matrix rho sub a, we can construct a pure state psi such that when we take the partial trace of this state over some subsystem B, it results in our density matrix rho sub a. And this procedure is known as purification. And what the HJW theorem tells us is that there are multiple states psi that will result in this density matrix rho sub a. And it also shows how they are related to each other. So this is another way in which this density matrix representation is ambiguous, but again, it's very closely related to the one we described with ensembles. So this is clearly something very important to keep in mind when dealing with density matrices.